Hi everybody, welcome to Dr. Manny's YouTube Learn Shops. This session will deal with descriptive statistics, and this will be part 1, which deals with measures of central tendency. So the learning objectives are to describe the properties of central tendency, variation and the shape in numerical data. Calculate descriptive summary measures for a sample, and construct and interpret a box and whisker plot. However, remember, you can always look for further resources on the internet. There are some very good YouTube videos that describe the process very simply. So descriptive statistics then is, as an overview, it's a branch of statistics that aims at describing, descriptive, a number of features of the data usually involved in a study. The main purpose is to provide a brief summary of the samples and measures done on a particular study. Descriptive statistics reduce the data into a simpler summary because it can be quite complex. For example, consider a simple number used to summarize how well a footballer is performing. His goal score average is 10. This single number 10 is the number of goals divided by the number of times he tries the attempt, 50. So 50 divided by 10, 50 attempts, 10 successes equals 20% of his score average. Descriptive statistics can be measures of central tendency, which is the mean, mode and median, or a measure of variability, which can be the range, mode and standard deviation. Taking it further, descriptive statistics, as we said, as measures of central tendency, can involve the mean, median, mode, quartiles, and variation or measures of dispersion, standard deviation, variance and range. So what are the functions of descriptive statistics? Well, they enable the presentation of raw data in a more meaningful way, which allows simpler interpretation of that data. If the raw data was presented, it would be really hard to visualize in most cases what the data was showing. So this involves methods that use tables, graphs and summary measures to organize and describe and display the data. So you can have raw data there, for example, and then much simpler to see it in a pie chart, for example. Makes it simpler to view. Then you've got analytic techniques with descriptive statistics. And these are measures of central tendency, which just mean middle values, the mean, median and mode. Or measures of variation, which is the differences in groups, range, variance, standard deviation. Or measures of frequency. These are counts, percentages and frequencies. Or measures of position, percentile ranks and quartile ranks. So let's introduce. A measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within the data set. The measures of central tendency are sometimes called measures of central location and are classed as summary statistics. The mean is often called the average, and it's the most common measure of central tendency. But there's also the median and the mode. The mean, median and mode are all values, valid values or measurements of central tendency. But under different conditions, one may become more appropriate than another, as we'll see. So measures of central tendency then basically are mean, median and mode. And the central tendency measures is a defined number that represents the center or middle of a set of data values. And as we said, the three common ones are, and repetition will be good to reinforce the information you're gaining, The three commonly used measurements of central tendency are mean, median, and mode. The mean is the arithmetic mean, the mathematical mean, and it's the simplest and most widely used measure of mean or average. It simply involves taking a sum of a group of numbers, then by dividing it, that sum, by the count of the numbers used in a series. Mean equals the sum of all data points divided by the number of all the data points. The mean is the average, and as I said, it's the most common measure of central tendency, and it's used with both discrete and continuous data, although most often with continuous data. The mean is equal to the sum of all the values in a data set, divided by the number of values in the data set, as we said. So for example, if we have n values in the data set, and they have values 1, 2, xn, the sample mean usually is denoted by x or x bar. The mean is the average, and this is the formula that is usually written in a slightly different manner using the Greek capital letter sigma, pronounced sigma, which means in Greek sum of. There are issues with the mean. The mean has one main disadvantage. It's particularly susceptible to the influence of outliers. And outliers essentially are values that are unusual compared to the rest of the data set, because they can be particularly small or large in numerical value. So for example, consider the wages of 10 staff at UniMass. 1 15k and 10 95k. The mean salary for these 10 staff is 30,000.7k. However, the raw data suggests that this mean value might not accurately reflect the typical salary of the staff, as most of the salaries are in the range of 12 to 18k. The mean is being skewed by two large salaries. Therefore, taking the median would be considered a better measure of central tendency in this situation. Let's review an activity relating to the mean. The grading marks of 5 students in a mathematics examination with a maximum possible mark of 20 are given below. 14, 12, 18, 17, 13. You have to find the mean grade mark for these 5 students. That's the formula. That's the solution. So the mean grade mark is 14.8. The median is the middle value of the data set, and it's arranged in an ascending order of size or magnitude. The marks of 5 students in a chemistry exam, for example, which has a maximum grade of 20, are given below: 18, 15, 19, 17 and 14. You arrange it in an ascending order, so therefore the median is 17. The middle value. The median can have an even or an uneven data set. So let's look at the even data set first. So when you're looking at the median with an even data set, this formula works typically better when you've got an odd number of scores. But what happens if you have an even number of scores? So for example, what if you had 10 scores and even data set values? Have a look. Simply take the 2 middle scores and average the result. So the data set here, 55 and 56. both the 5th and 6th scores are averaged, so the median becomes 55.5. In an uneven data set, which is simpler, the median is the middle score for a set of data that's been arranged in an order of magnitude. The median is less affected by outliers and skewed data. In order to calculate the median, suppose we have the data below. The middle value is 56. So the median is the middle value of the data set arranged in order of the magnitude. 56 is the median. So let's review the median activity. The marks of 5 students in a chemistry exam, which has a maximum grade of 20, is given below. Arrange them in an ascending order. Find the median grade mark. So you arrange the marks in ascending order of magnitude, 14, 15, 17, 18, 19. The third value is 17, and it's the middle one, so the median is 17. Now let's look at the mode. The mode is the most frequent score in our data set. That's basically what it is. On a histogram, it represents the highest bar in a bar chart, or histogram. Therefore, consider the mode as being the most popular option. The mode normally is used for categorical data, where researchers want to know which is the most common category. For example, the most common form of transport in this data set is the bus. An issue with mode, however, is that it's not unique. That leaves researchers with problems when there are 2 or more values that share the highest frequency. This is a problem, especially when we have continuous data, because it's more likely not to have any one value that is more frequent than another. So consider, you're measuring 30 people's weight to the nearest 0.1 kg. It's a small sample. How likely is it that we find 2 or more people with exactly the same weight, for example, 67.4 kg? The answer is probably very unlikely. Many people might be close, but with such a small sample, 30 people, and a large range of possible weights, it's unlikely to find 2 people with exactly the same weight to the nearest 0.1 kg. Another problem with mode is that it doesn't provide a very good measure of central tendency when the most common mark is far away from the rest of the data in the data set. This is illustrated in the histogram below. The mode has a value of 2, however, the mode is not representative of the data, which is mostly concentrated around 20 to 30 value range. To use the mode to describe the central tendency of this data would be misleading. It would be incorrect. So let's review mode. What is the mode for the numbers indicated here? 7, 6, 5, 8, 7, 5, 9, 3, 5, 4. The solution is to put the numbers in order first. And which one occurs the most often? That's what we said. It's the most popular. The most popular choice. So 5 occurs most often, so mode is 5. Another review activity. What's the mode for the numbers 7, 6, 5, 8, 7, 5, 9, 3, 5, 7? The solution is put the numbers in order first. So 5 occurs 3 times, and so does 7. So there are 2 modes, 5 and 7. Bimodal. When we then look, we mentioned the term skewed. Skewed distributions in relation to normal distributions, mean and median. Researchers often test whether data is normally distributed because this is a common assumption underlying many statistical tests. When you have a normally distributed sample, you can use mean or median as your measure of central tendency. In any symmetrical distribution, the mean, median, and mode are equal. The histogram is an example of a normally distributed set of data. Look at the histogram. If the data is skewed to the right, in this situation, the mean is the best measure of central tendency. It's the measure that includes all the values in the data sets for its calculation, and any change in the scores will affect the value of the mean. However, this is not the case with the medium or the mode. So in summary, when do you use the mean, the medium, or the mode? It depends on the type of variable. So with a nominal variable, the mode is the best measure of central tendency. For an ordinal variable, the medium is the best measure of central tendency. When we're looking at the interval or the ratio that's not skewed, the mean is the best. When we're looking at the interval and the ratio and it's skewed, the medium is the best. Let's review. When is the mean the best measure of central tendency? The mean is usually the best measure of central tendency when the data distribution is continuous and symmetrical, such as when your data is normally distributed. Okay, another activity for you. When is the mode the best measure of central tendency? The mode is the least used of measures of central tendency and can only be used with nominal data. The mode will therefore be the best measure of central tendency as it's the only one appropriate to use with nominal data. What's your hair colour? What's your gender? Another review activity. When is the medium the best measure of central tendency? The medium is usually preferred to other measures of central tendency when the data set is skewed or the researcher is dealing with ordinal data. Ordinal data, a scale, in an order. How do you feel today? How satisfied are you with our service? So it can be right-skewed, which is also referred to as positive skewness, or it can be left-skewed, which is referred to as negative skewness. It's used with ordinal data. What about in this situation? In a normally distributed data set, which is greater, the mode, medium, or mean? Look at the diagram. If the data set is perfectly normal, the mean, medium, and mean are equal to each other. They have the same value. In a normally distributed data set. So let's look at the empirical relationship of the mean, medium, and mode. It's a frequency distribution that has a symmetrical frequency curve. The empirical relation states mean equals the medium, which equals the mode. Empirical relationship number 2. The empirical relationship states a frequency distribution that has an asymmetrical, positively skewed, right-skewed, frequency distribution curve is as follows. The mean is greater than the medium, which is greater than the mode. Empirical relationship number 3 states that a frequency distribution that has an asymmetrical, negatively skewed, left skew, frequency distribution, the curve is as follows. the mean is less than the median, which is less than the mode. So in summary, for this component of this session, in statistics, the mean, median and mode are typical values to represent a large amount of numerical observations, and they are calculated from numerous observations. The mean is the average of all the values. The median is the middle value dividing the number of data into two halves. In other words, 50% of the observations are below the median and 50% of the observations are above the median. The mode is just the most common value among all the given observations. Now the next component of this session are looking at variability. Now variability is defined or defines how far away the data points tend to fall from the centre. Median, mode, mean. Variability refers to the spread of the set of data, and variability in the context of distribution of values is also called spread or dispersion. Measures of variability can include range, interquartile range, variance, standard deviation, and coefficient of variation, which we're not going to be reviewing. You can review if you choose to. Variability describes how far apart data points lie from each other and from the centre of the distribution. And this is most commonly measured with range, interquartile range, standard deviation, and variance. Range, the difference between the highest and lowest values. Interquartile range, the range of the middle half of the distribution. Standard deviation, the average distance from the mean. Variance, the average of the squared distances from the mean. So, as we said, measures of variability include range, the difference between the highest and lowest values. The interquartile range, the range of the middle half of the distribution. The standard deviation, the average distance from the mean. And the variance, the average of the squared distances from the mean. Why is variability important? Well, variability serves both as a descriptive measure and as an important component of inferential statistics. In the context of inferential statistics, which we'll be covering later, variability provides a measure of how accurately any individual score or sample represents the entire population. Why does variability matter? Well, while central tendency or average, the mean, tells you where most of your points lie, variability summarizes how far apart they are. This is important because it tells you whether the points tend to be clustered around the center or more widely spread out. Low variability is actually ideal because it means that you can better predict information about the population based on the sample data. High variability means that the values are less consistent, so it's harder to make predictions. Data sets can have the same central tendency but different levels of variability or vice versa. If you know only the central tendency or the variability, you can't say anything about the other aspect. Both of them together give you a complete picture of the data. So here's an example of variability in normal distributions. You're investigating the amount of time spent on phones daily by different groups of people. Using simple random samples, you collect data from three groups. Sample A, high school students, sample B, college students, sample C, adult full-time employees. So when you look at all three samples, they have the same average mobile phone use, which is 195 minutes. Although the data follows a normal distribution, each sample has a different spread. Sample A has got the widest spread, or largest variability. Sample C has got the smallest spread, or smallest sample variability. Range is the simplest measure of variation. It's the difference between the largest and the smallest observations. Range, typically x here, you can have the largest minus x being the smallest. So for example, from 1 to 14, that's the range. Smallest being 1, the largest being 14. The method in relation to the range is you can find the range by subtracting the smallest number from the largest. For example, if you earn $250 in a week, 30 in the second week, 800 in the third week, the range for your pay, how much it varies, is 30 to 800. The range tells you the spread of your data from the lowest to the highest value in the distribution. And it's the easiest measure of variability to calculate. To find the range, simply subtract the lowest value from the highest value in the data set. The disadvantages are, however, it ignores the way in which the data are distributed, and it's very sensitive to outliers. The outliers in this case being 1 to 120. So an example of range, you've got 8 data points from your sample. 72 being the lowest, 324 being the highest, which you end up with a range now of 252 in the data set. But because only 2 numbers are used, the range is influenced by the outliers, lowest 72 and highest 324. And it doesn't give you the information about the distribution values. It's best used in combination with other measures rather than in isolation. Then you've got interquartile range. And this can eliminate some of the problems related to range in relation to outliers. And it eliminates the high and low value of observations. And it calculates the range of the middle 50% of the data. Interquartile, third quartile minus first quartile. So the interquartile range equals the third quartile minus the first quartile. The interquartile range is a measure of variation for interval and ratio data, and it indicates the width of the middle 50% of the distribution, closer to the median. It's defined as the difference between the lower and upper quartiles. And the third quartile is the 75th percentile, and the first quartile is the 25th percentile. The interquartile range is the range that shows the spread of the whole data set. The interquartile range shows the spread of the middle half of the distribution. The interquartile range contains the second and third quartiles, or the middle half of the data set, the median. And the rationale for its use is that it's useful to measure variability for skewed distributions and data sets with outliers. For these distributions, the median is the best measure of central tendency because its value exactly in the middle, where all the values are ordered from low to high. And along with the median, the interquartile range can provide an overview of where most of the values are and how they're grouped. So how do you calculate it? Well, calculating the interquartile range, you subtract the quarterly 1, first quarter, value from the third quarter. And the formula is as is there. Interquartile range equals the third quartile minus the first quartile. The first quartile is the value below which 25% of the distribution lies, while the third quartile is the value below which the 75th of the distribution lies. So you can think of the first quartile as the median of the first half and the third quartile as the median of the second half of the distribution. In an even numbered data set, step 1 would be to order the values from low to high in an ascending manner. Locate the median and then separate the values below it from the values above it. With an even numbered data set, the median is the mean of the two values in the middle. So divide the data set into two halves. Step 3, find the first quartile and the third quartile. The first quartile is the medium of the first half and the third quartile is the medium of the second half. Each half has an odd number of values. There are only one value in the middle of each half. Then you calculate the interquartile range, which is 81 minus 57, which is equal to 24. In an odd numbered data set, step 1 would be again to order the values from low to high. Step 2, locate the median, then separate the values below it from the values above it. In an odd numbered data set, the median is the number of the middle of the order. The actual median is excluded from both halves. One half contains all the values below the median and the other half contains all the values above it. Step 3, you find the first quartile and the third quartile, and again the first quartile is the median of the first half and the third quartile is the median of the second half. Each of these halves have an odd numbered size. There's only one value in the middle, so you calculate the range similarly to what we did to the even. When we look at the interquartile range in box plots, well, first of all, what is a box plot? A box plot, or a box and whisker plot, is a tool that summarizes a data set visually using a 5-number summary. Every distribution can be organized using these 5 numbers. The lowest value, the first quartile, the medium, the third quartile, and the highest value. Vertical lines in the box show the first quartile, the medium, and the third quartile. The whiskers at the end show the highest and lowest values. So for clarity, let's explain. In a box plot, the width of the box shows the interquartile range. The small width means less dispersion, the larger which means more dispersion. Box plots are useful for showing the central tendency and the dispersion of skewed distributions. Negatively skewed, positively skewed. The placement of the box tells you the direction of the skew. The box that's much closer to the right means you've got a negatively skewed distribution, and the box closer to the left tells you that you have a positively skewed distribution. Okay, let's review. What's the difference between range and interquartile range? Well, the range gives you the spread of the whole data set. Interquartile range gives you the spread of the middle half of the data set. When should the interquartile range be used? The interquartile range is best measured of variability for skewed distributions or data sets with outliers. Because it's based on values that come from the middle half of the distribution, it's unlikely to be influenced by outliers. Now let's review measures of variability, variance. Variance is the average squared difference of values from the mean. This method is used to calculate a set of square differences between the data points and the mean sum of them, and divide them by the number of observations. This is the average square difference. There are 2 formulas for the variance, depending on whether you're calculating the variance of an entire population or a sample to estimate the population variance. Population variance, this is a measure of the spread of the population data and is defined as the average of distances from each data point in a particular population to the mean squared, and it indicates how data points are spread out in the population. Population variance is an important measure of dispersion which is used in statistics, and it's calculated by the following formula. The mean population the population size, and the value of the variable. The steps in calculating population variance or understanding it are: 1. Calculate the mean of the given data. In order to calculate the mean, add all the observations and then divide it by the number of observations, which is n. Step 2. Make a table, which isn't compulsory, but in tabular form it makes your calculations easier. In the first column, write each observation. For example, x1, x2. Step 3. In the second column, write the deviation of each observation from the mean. The deviation is xi minus the mean. Step 4. In the third column, write the square of each observation from the mean. In other words, square each of the numbers obtained in column 2. Step 5. Add the numbers obtained in the third column and find the sum of the squared observations and divide the sum by the numbers of observations. This is the population variance. Sounds complicated, but it isn't really. So if we have a look at it, an example in Excel, which is an inbuilt formula, and there will be a variation in SPSS. So when you do the practicals, you can determine this. So for example, a medical team recorded that 8 babies had been born in the first week of August 2021. The pediatrician wanted to evaluate the health of the babies as well as the variance in heights. The heights of these babies were 48, 47, 50, 53, 50, 52, 51, 60 centimetres. The variance of heights in these 8 babies are calculated as follows. And this is using the Excel inbuilt formula. So the population variance was 13.8, 13.98. The tools that we have in Excel and SPSS are very user-friendly. As I said, the population variance, 13.98. We use sample variance, as we've indicated previously, because it's impossible to measure an entire population. And statisticians use the following equation of sample variance. In the equation, sample variance is s to the power 2. Sample mean is x. The number is n. This is the denominator that corrects for the tendency of the sample to underestimate the population variance. So sample variance can be calculated using the following formula. The arithmetic mean, the sample size, and the variability. An example. Calculating sample variance using the formula for sample on the data set with 17 observations in the table on the next slide. Because the calculations use the square differences, the variance is in squared units rather than original units of the data. While the higher values of the variance indicate greater variability, there is no intuitive interpretation of specific values. Despite this limitation, various statistical tests use the variance in their calculations. For example, the F-test and ANOVA, which we'll be covering as we go through this course. While it's difficult to interpret the variance itself, the standard deviation resolves this problem. Using the formula for a sample on the dataset of 17 observations in the table, the numbers represent the table column number. Take each observation 1. Subtract the sample mean 2 to calculate the difference in column 3. Square the difference 4. Sum the square differences at the bottom of the table. Then take the sum and divide by 16 because the sample variance equation used 17 observations. 17 minus 1 equals 16. The variance for the data set is 201. When we measure variance, we also use standard deviation. And standard deviation shows the spread of the data, the distribution of the data. And it's a measure of how far each observed value is from the mean. In any distribution, about 95% of values will be within 2 standard deviations of the mean. When calculating the standard deviation, it's rarely calculated by hand. However, it can be done using the following formula, where x represents a value in the data set. You've got the mean and the number of values in the data set. There are 2 types of standard deviations, the population standard deviation and a sample deviation. And they both follow the same steps here. Most commonly used measure of variation. They show variations about the mean, and they both have the same units as in the original data. When calculating the standard deviation, it's got generic steps. Step 1, calculate the mean. Step 2, subtract the mean from each value to obtain the deviations from the mean. Step 3, square each of the deviations. Step 4, add together all of these square deviations. But now, the calculation of these standard deviations differs. If calculating the population standard deviation, then you divide by n, the number of data values. If calculating the sample standard deviation, then you divide by n minus 1, one less than the number of the data values. So to compare these 2 calculations, we'll start with the same data set, 1, 2, 4, 5, 8. Next, perform all the steps that are common for both calculations. Step 1, the mean is 4. Step 2, the deviations are found by subtracting the mean from each value, which you can see there, minus 3, minus 2, 0, 1 and 4. Step 3, the deviations are squared as follows, 9, 4, 0, 1, 16. Step 4, now we add these square deviations to see their sum, and the sum is 30. Now in step 5, in the first calculation, we treat the data as if the entire population. We divide the number of data points, which is 5. This means the population variance is 30 divided by 5, which is 6. The population standard deviation is the square root of 6. This is approximately 2.4495. In the second calculation, we treat the data as if it's a sample and not the entire population. We divide by 1 less than the number of data points. So in this case, we divide by 4. This means that the sample variance is 30 divided by 4, which is equal to 7.5. The standard sample deviation is the square root of 7.5. This is approximately 2.7386. So in this example, there's a difference between the population and the sample standard deviations. When we look at the distribution in statistics, this is a set or a population showing all the possible values or intervals of the data and how often it occurs. Distribution of categorical data is organized. You see the number or percentage of individuals in each group. Distribution of numerical data is also organized. They're often ordered from smallest to largest and broken or categorized into reasonably sized groups and then put into graphs and charts to examine the shape, center and amount of variability. Let's see what we mean by shape of distribution, or the shape of a distribution data set. And this is typically characterized by looking at its histogram. Data values can be in a single pile, which is called unimodal. 2 piles, bimodal. If it's symmetrical, it's bell-shaped, or it has a different shape. If there's a tail in the distribution, it's skewed. Large data values, the distribution is skewed right, or it can be positive. Small values, the distribution is skewed left or negative. A distribution where each rectangle is the same height has a uniform distribution. They can be symmetrical, uniform, bimodal, skewed left and skewed right. A normal distribution is also known as a bell curve, and this is the most common frequency distribution. Symmetrical, the bell curve. The empirical rule that's associated with this is that the statistical rule, also known as the 3 sigma rule or the 6895 99.7 rule, this states that for a normally distributed data, almost all the data will fall within 3 standard deviations, either side of the mean. 68% of the data within 1 standard deviation. 95% of the data within 2 standard deviations. 99.7% of the data within 3 standard deviations. The empirical rule algorithm is as follows, which you don't have to memorize. You calculate the mean of your values, you calculate the standard deviation, you apply the empirical rule formula, and then you enter the mean and standard deviation into the empirical rule calculator app, which is available on the internet, and it will output the intervals for you. How to use the empirical rule. Here's an example. IQ scores are normally distributed with a mean of 100 and a standard deviation equal to 15. Using the 689599 rule calculator app, which you can on the internet, this is what you would do. The mean, 100, standard deviation, 15, the empirical rule, 100 minus 15 equals 85, 100 plus 15 equals 115. 68% of people have an IQ between 85 and 115. 95% of people have an IQ between 70 and 130. And 99.7% of people have an IQ between 55 and 145. For a quicker, easier calculation, input the mean and standard deviation into the empirical rule calculator app and watch as it does the rest for you. There are so many tools available on the internet that help you with statistical analysis. However, if you really are using statistics and you're not sure, a statistician would be the person to go to. So let's review. When is the mean the best measure of central tendency? The mean is usually the best measure of central tendency to use when your data distribution is continuous and symmetrical, such as when your data is normally distributed. However, it all depends on what you're trying to show from your data. The demand for a product on each of 20 days was as follows in units. Calculate the arithmetic mean. The arithmetic mean is 9.25 units. I know I'm rushing you, but it's just an example. The following table shows the annual wages of 200 employees in an engineering firm. Calculate the mean, median, and mode of the annual wages. You can do this with your PDF version. The mean is 6262.5, the median 6263.1, the mode 6260.9. So in summary, central tendency is very useful as it identifies what is normal or average for a set of data. It condenses the data set down into one representative value, which is useful when working with large amounts of data. The measures of central tendency allow researchers to determine the typical numerical point in a data set. Measures of central tendency tell researchers where the center value lies in the distribution of data. From a statistical perspective, The average refers to the arithmetic mean. The concept of average is an easy way to think about what measures of central tendency say about the data. While central tendency tells you where most of your data points lie, variability summarises how far apart your points are from each other. Data sets can have the same central tendency but different levels of variability and vice versa. Together, they give you a complete picture of your data. Okay, that concludes this session in an introduction to the basics. There are 7 other parts to this basic statistics learn shop. And remember, it is just the basics. And you can get access to a lot of other information on some of the excellent YouTube videos. See you in the next session, and if you think this has been of any value to you, or any of the other Dr. Manny Learn shops, recommend them to your friends and colleagues. Thanks, see you soon.